So this lesson is a continuation of yesterday's. We need one more time for adding and subtracting by multiplying first, and you'll see why in our first example, why that's necessary. So here everything's lined up. The x's are lined up, y's are lined up, constants are lined up. That's perfect. But the problem is, if I multiply, there's nothing I can multiply the first equation by, and by first equation by, I mean this one. There's nothing I can multiply that by so that 2 equals 7, or that 9 equals 12. And so we're a little bit stuck there. And there's nothing I can multiply the second equation by so that 7 would equal 2, or that 12 would equal 9. So in this case, what I actually need to do is I need to multiply both equations. And I'll just show you the first example, and then in the next one, you'll see what I'm talking about. So 2 and 7, I can make them both 14. So that's what I'm going to do. So I'm going to multiply the first equation by 7, and I'll multiply the second equation by 2. And so I get 7 times 2x is 14x minus 63y equals 7. And for the second equation, I get 2 times 7x is 14x minus 24y equals 46. And you see right away, we accomplished our goal of getting one of the variables to have the same coefficient. Both of the x's have a coefficient of 14, so we can get rid of that by eliminating. So now we just have to ask ourselves, we're going to add or subtract. And so if I did 14x plus 14x, I'd get 28x, not what I want. So we're going to subtract the second equation from the first. So 14x minus 14x is 0, so that's perfect. Negative 63y minus a negative 24y is the same as negative 63y plus 24y. So that will be negative 39y. And 7 minus 46 is negative 39. So divide by negative 39, and we get y equals 1. So we have a y value, and like we have it in every other example, we'll pick one of the equations to plug that back into to find our x value. So we can plug that in. So we get 7x minus 12 instead of y, and multiplying by 1 now, equals 23. So 7x minus 12 equals 23. And if I add 12 to both sides, I get 7x equals 35. And if I divide by 7, I get x equals 5. And so now my solution, remember, is always the point. It's the point where the two lines intersect. So 5, 1 is my answer. So a few things when we're trying to find common multiples. If you're ever stuck, the easiest thing to do is just to multiply the two numbers. So in that case, we had 2 and 7. If you do 2 times 7, you get 14, and that's exactly what we ended up doing. Okay? So it doesn't always give you the least common multiple. So for instance, I'll do 6 times 15, and that's 6 times 10 is 60, 6 times 5 is 30, so that's 90. But I know that 6 can go into 30, and I know that 15 can go into 30. So when you just multiply them, it'll work, but you might not get the least common multiple. And that's not really a big deal. But if you do want to find the least common multiple, there's a couple techniques we can review really quickly. So let's stick with our 6 and 15 example. So we can list the multiples of each until we find a match. And what we mean by that is we can do 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, times 4 is 24, times 5 is 30, times 6 is 36, and so on and so forth. And for 15, it'd be 15 times 1 is 15, 15 times 2 is 30. And so I already see right now I have a match in both lists. And so that means it's a common multiple. And since it's the first one, it's the least common multiple. So 30 is the least common multiple between 6 and 15. The other thing we can do is use a factor tree. So I know I have 6 and I have 15. And to get 6, I multiply 2 times 3. I need those factors. And for 15, I multiply 3 times 5. And so what I need to find now are all the common factors that I need. So 6 needs a 2 and a 3, so I'll multiply that. Now 15 needs a 3, but I already have it, so I don't need to write another one. But I do need the 5 since we don't have a 5 yet. So now 2 times 3 is 6, times 5 is 30. So either way, we're going to get the same thing. What you'll notice though is if it ends up being a large number, the factor tree will still get you there really quickly. Whereas listing the multiples, you could be doing that for a little while. So this is This is definitely the fastest way to do it if you need to, and probably the most effective. But back to the main point. So it doesn't actually matter if you find the least common multiple. As long as you find any common multiple, the process is going to work just fine. But the advantage of finding the least common multiple is just that smaller numbers are generally easier to work with. And so that gives you probably a smaller chance that you're going to make some computational error. So if you have it, it's a benefit, but it's not necessary to solving the problem. So we'll do one more. And as you can notice here, here's another example where we don't have any alignment. Our x's aren't aligned with the x in the second equation, the y's aren't aligned, the constants aren't aligned. So we need to move these things around so that everything's all aligned. So what I'm going to do here is I'm going to take the 3x and I'm going to move it to the left side so that the x's and y's are both on the left side as they are in the first equation, and then we'll have the constant left. So to do that, I'm going to subtract 3x from both sides. And since I want the x's first to line up with these x's, I'll write those first. So I have negative 3x. The y's are positive, so plus 2y. And what's left over here is just that negative 9. And I'll bring down the first equation just so we have everything lined up. So I have my 4x plus 5y equals 35. Okay, so now step 2, we can see the problem again is none of the coefficients are the same. For x's, I have negative 3 and 4, can't eliminate. For y's, I have 2 and 5, can't eliminate. And there's nothing I can multiply the 3 by to make it 4, and there's nothing I can multiply the 2 by to make it 5. So I have to multiply both equations, and I have a couple options. I could multiply the x's so that they're both 12, because I know 3 and 4 are both going to 12. Or I could multiply the y's so that they're both 10, because I know that 2 and 10 and 5 will both go into 10. And that's what I'm going to do. So I'll multiply the first equation by 5, because my goal is to make this 10y. And I'll multiply the second equation by 2, because my goal is to make this 10y. So 5 times negative 3x is negative 15x. 5 times 2y is plus 10y. And 5 times negative 9 is negative 45. And now my second equation, 2 times 4x is 8x. 2 times 5y is plus 10y. And 2 times 35 is 70. And right away you can see we accomplished our goal because we have the 10y's are the same, so we can eliminate that. So I need to get rid of it. So 10y minus, we're going to subtract the second equation from the first. 10y minus 10y will cancel out. So negative 15x minus 8x is the same as negative 15x plus negative 8x, and so it's negative 23x. 10y minus 10y cancels out. And negative 45 minus 70 is the same as negative 45 plus negative 70. So it's negative 115. And I'll just divide both sides by negative 23. And that is 5. So x is 5. And as we've done in all of our other examples, I just need to go and plug this into either of my first equations to get the matching y value. So I know that 4 times 5, because that's our x value, plus 5y equals 35. So it's 20 plus 5y is 35. And so I'm going to subtract 20 from both sides. And so 5y equals, there we go, 15. Divide by 5. And y is 3. And so again, our solution is the point, and every point has an x and a y value, so we need to write both. So 5, 3. And if you go to Desmos and you graph these two equations right there, you will find that they intersect at 5, 3. So the last set of problems for adding and subtracting to solve the linear systems is page 455, 10 to 24 evens, and the challenge is 33. Good luck.